Welcome to lesson number 21 on probability from Actuarial Path. In this lesson we study the exponential distribution, which is used very often in different applications in engineering and in insurance and so on. In engineering, they typically use it to model time to failure of machines or components of a machine or a computer and so on. In actuarial science, an actuary may be interested in modeling the time to an accident or the time between consecutive accidents. If a random variable x follows an exponential distribution with parameter lambda, exponential distribution has only one parameter. Its PDF, the probability density function of an exponential random variable, is given by lambda times e to the negative lambda times x for values of x greater than or equal to 0, or the PDF is 0 otherwise. Okay, and lambda is greater than 0. Definitely the support is greater than or equal to 0 because exponential distribution, as we said, is used to model time to failure. Time until something happens has got to be positive or 0. It cannot be negative. If this is a valid PDF, then we should have the integral from 0 to infinity of f of x dx be equal to 1. Let's see if that is true. So that integral is the integral from 0 to infinity of lambda times e to the negative lambda times x dx, which is equal to lambda times e to the negative lambda x times minus 1 over lambda, limits from 0 to infinity. I can rewrite this as, you can cancel the lambdas, take out the negative outside, and then I have e to the negative lambda times x, lower limit 0, upper limit infinity. When x approaches infinity, as x goes to infinity, what you have here is e to the power of negative infinity, which is going to be equal to 0. So this is equal to 0 minus, and when x approaches 0, this expression e to the negative lambda times x goes to 1. Therefore, this is equal to 1, telling us that the exponential PDF integrates to 1. Okay, what I'm going to do next is find the expectation. Actually, let me do the CDF, the cumulative distribution function, the CDF of the random variable x, which is exponential with parameter lambda. The CDF is the probability that x is less than or equal to little x. Definitely, if little x is less than 0, the CDF is equal to 0, because the PDF is not valid for values of x less than 0. So this is capital F, which is the usual notation for CDFs. This is going to be equal to 0 for values of x less than 0. But what is the value if x is greater than or equal to 0? Alright, if x is greater than or equal to 0, the CDF is equal to the integral from 0 to x of f of u du, which is equal to the integral from 0 to x of lambda times e to the negative lambda times u du. Again, very similar integration that we did here, except the limit of integration now changes from 0 to infinity to 0 to x. So this is simply equal to, you can do the integration, this is a very simple integration, e to the negative lambda times u, lower limit 0, upper limit x. So when u approaches to x, this is going to be equal to e to the negative lambda x, and when u goes to 0, this is going to be equal to 1 minus 1. So the CDF is 1 minus e to the negative lambda x for values of x greater than 0. So I can write this here. 1 minus e to the negative lambda times x. Let's find the expectation of this random variable x. So the expectation of x is equal to the integral 0 to infinity of x times f of x dx, which is equal to integral 0 to infinity of x times lambda times e to the negative lambda x dx. We're going to apply integration by parts here. So I'm going to let u to be equal to lambda times x, and dv, the differential dv, to be equal to e to the negative lambda x dx. So that integral is simply the integral of u dv. And integration by part tells us that this is equal to u times v minus the integral of v du. So we need to find du and v. But from here, du is lambda times dx. And v, the antiderivative of that, is equal to minus 1 over lambda e to the negative lambda x. Apply now integration by parts. We have u times v. U is equal to lambda times x times v is minus 1 over lambda e to the negative lambda x. So I'm going to take the negative here. Then I have 1 over lambda e to the negative lambda times x. Now limits from 0 to infinity minus v integral minus the integral of v du. V is minus 1 over lambda e to the negative lambda x. Du is what? Du is lambda dx. Now this is from limits from 0 to infinity. Okay, let's cancel out things, write it in a nicer way. So this is going to be equal to minus, the lambda cancels out, lambda by lambda. So we have x times e to the negative lambda x, lower limit 0 and upper limit infinity. We have minus here and minus here, so I can write a plus. Integral 0 to infinity, and lambda here cancels this lambda, so I would only be left with e to the negative lambda x dx. Okay, what happens to x e to the negative lambda x when x approaches infinity? Alright, let's see that. The limit as x goes to infinity of x times e to the negative lambda x. I can rewrite this as the limit as x goes to infinity of x divided by e to the lambda times x. When x goes to infinity, the numerator, which is x, definitely goes to infinity. Also, the denominator goes to infinity. E to the lambda x goes to infinity as x goes to infinity. So we have infinity divided by infinity, which is an indeterminate form. So when we have such forms, what we do is we use L'Hopital's rule from calculus. L'Hopital's rule is simply take the derivative with respect to x of the numerator and also the denominator, and then take the limit afterwards. So this is equal to the limit as x goes to infinity. The derivative of the numerator with respect to x is 1, and the derivative of the denominator with respect to x is lambda times e to the lambda x. And now we don't have an indeterminate form. We don't have infinity over infinity or something like that. So we can take the limit, a constant divided by something which goes to infinity as x goes to infinity gives us a 0. Okay. So we have this equal to minus 0 minus, when x goes to 0, this is 0 times e to the negative lambda to the power of 0. 0 times any number is going to be 0. So this is 0 minus 0, which is 0. So this term actually entirely goes to 0. So we are left with only the second integral term, which is integral 0 to infinity of e to the negative lambda times x dx. You can do the integral. This is a very simple integration, but there's a simpler way of doing this, which is multiply this by lambda and also divide it by lambda, so nothing changes. And you see that that expression is the integral of an exponential PDF. This is what you should be very good at in probability. Recognize that this is a PDF of an exponential distribution, so therefore it must integrate to 1. Okay? So that goes to 1. What I have in circle here in black goes to 1, so I have 0 plus 1 over lambda times 1, which is 1 over lambda. So the expectation of the exponential random variable x is equal to 1 over lambda. I think this is a very tedious way of doing the expectation. We have a nicer way of finding the expectation, which is what I'm going to do next. That involves using the moment generating function of an exponential random variable. Now let's find the MGF. The MGF is equal to mx of t is equal to the expected value of e to the power of t times x, which in this case is equal to the integral from 0 to infinity of e to the tx times the PDF lambda e to the negative lambda x dx, which I can rewrite as the integral 0 to infinity of lambda. Combine the powers here. E to the, what do I have? I have minus lambda x plus tx dx, which you could combine, again, simplify as lambda e to the power of minus lambda minus t times x dx. Take out this lambda outside of the integral, so you have lambda times the integral 0 to infinity of e to the power of negative lambda minus t times x dx. Now you recognize this looks like the PDF of an exponential distribution with parameter lambda minus t. So if I multiply this by lambda minus t, then this integral should be equal to 1 because I am integrating an exponential PDF. You need to be good at this. That's one of the major tricks in probability distribution theory. But since I multiplied this by lambda minus t, I need to divide it by lambda minus t so that nothing changes. Okay, so the quantity doesn't change. So this is equal to lambda divided by lambda minus t multiplied by 1. So this PDF integral is equal to 1. So we have the MGF, and once you have the MGF, it's a matter of doing derivatives to find the expected value and the variance and so on. So the expected value of x is now much easier to find because you just need to find the derivative with respect to t of lambda minus t, which is the MGF, and evaluate that at t equals 0. The derivative of the MGF evaluated at a value of t equals 0. So this is much easier to deal with than doing integration by parts. That's just my opinion. But there's so many different ways of doing the same thing. Doesn't mean one is wrong. It means that some are easier than the others. So for you, you could, when you solve problems, especially in exam settings, you want to find the quickest way possible to do a problem so that you don't waste your time. Okay, so let's find this derivative, and that derivative is equal to lambda, actually negative lambda, times lambda minus t square. But then I have to take the derivative of lambda minus t by chain rule, and the derivative of lambda minus t with respect to t is negative 1. So multiplying this by negative 1 simply make this a plus. So I can get rid of the minus and evaluate this at t equals 0. and that is equal to lambda divided by, that looks like an x, oh, lambda divided by lambda minus 0 square, which is lambda square. That gives you 1 over lambda. So we found the expectation using the MGF technique, which I think is much simpler to do. Likewise, when you find the second moment, expected value of x squared, you can use the formula, the integral 0 to infinity of x squared f of x dx, which is lambda e to the negative lambda x dx. If you follow this route, you're going to have to use integration by parts twice to solve this integral, which is fine, it's not a problem, but it's much quicker to use the MGF technique. If you do that, the expected value of x squared is the second derivative, so d squared dt squared, of the moment generating function evaluated at t equals 0. Now, this is the first derivative of the MGF. So to find the second derivative, you simply take the derivative of the first derivative of lambda divided by lambda minus t squared, and then evaluate that at t equals 0. And that gives you minus 2 lambda divided by lambda minus t to the power of 3. Now times the derivative of lambda minus t with respect to t, which is negative 1. So when you multiply by negative 1, you simply could cancel that negative to be positive and evaluate that at t equals 0. So when you plug in t equals 0, you get 2 lambda divided by lambda to the power of 3, which is 2 over lambda squared. And therefore, the variance is the second moment, which is 2 divided by lambda squared, minus the square of the first moment, which is 1 over lambda, the whole quantity squared, which is equal to 2 over lambda squared minus 1 over lambda squared, which is 1 over lambda squared. So for an exponential distribution with the rate parameter lambda, the expected value is 1 over lambda, and the variance is 1 over lambda squared. So the variance is the square of the expected value. Okay. Memoryless property of exponential distribution. This is the last thing we want to do in this lesson. Memoryless property. Exponential random variable is the only continuous random variable which has this property, which I'm going to describe right now. Suppose you have a random variable x which follows an exponential distribution with rate lambda. Okay? And think of this random variable as the lifetime of an equipment or a machine. Okay? Since lifetime distributions are typically non-negative, I'm going to draw a number line starting from 0. Okay, say that's 0.0. Suppose this point is point s. So this length from 0 to s is s units of time. And let's say this point here is s plus t. So this interval from this point to that point has the length of t units of time. The question I want to ask is, what is the probability that this equipment will be functioning or will be functional after time t plus s? That is, the probability that x is greater than s plus t, given that it was functional, or given that it is functional after time s, given that x is greater than s. Another way to express this is, if I tell you that this machine has been working or has been operational until time s, what is the probability that it will be operational for at least additional t units of time? So that's what this probability is asking. And memoryless property says that it doesn't matter how long this equipment has been operational. So it does not remember this past. So calculating this probability is the same as calculating the probability that a brand new equipment of the same type is going to work for at least t units of time. So what you need to calculate is the probability that a new equipment would work for at least t units of time. And this probability will be equal to the probability that x is greater than t. Okay? So let's see if this property is satisfied for exponential distribution. So let's calculate the probability that x is greater than s plus t, given x is greater than s. This is equal to the probability that x is greater than s plus t, and x is greater than s by conditional probability formula divided by the probability that x is greater than s. This is equal to, what is the intersection of these two events? X greater than s plus t and x greater than s. Since s plus t is greater than s, then the intersection of these two events is x greater than s plus t. So that's the numerator, and the denominator would be the probability that x is greater than s. And we know for exponential random variable x, the probability that x is greater than little x is equal to 1 minus the probability that x is less than or equal to x. And this is the CDF. So that gives us 1 minus e to the negative lambda x, which is equal to e to the negative lambda times x. This is sometimes called the survivor function. Okay? The survivor function is the probability that random variable is greater than any value x. So the probability that x is greater than s plus t is e to the negative lambda times s plus t. And the probability that x is greater than s is e to the negative lambda times s. You could simplify this. The numerator is e to the negative lambda times s minus lambda times t. You can combine the power, move this one up, so you get minus, which would be a plus, lambda times s. So this simplifies to e to the negative lambda times t, which is equal to the probability that x is greater than t. Therefore, we have the memoryless property.